Hey, all right. So, talk number two, continuous delivery with containers. I'm Nick Gauthier. I work at Codeship. We've got a booth out there. You can chat with Kurt if you want to talk about Codeship, and of course, you can always chat with me about it. We do continuous integration and delivery, and personally, testing has always been really important to me going back through my entire career, so it's something I'm really passionate about. So, bringing that forward into the new world of containers, we're going to talk about how to do that with all this new great tech we've been playing around with so far the past 2 days. So I want to start off just talking about what continuous delivery is. Give a brief introduction so everybody knows what I'm talking about. If you've heard it before, that's all right. We're not going to spend too much time explaining it, but I want to make sure that we're all on the same page here. So I like this quote. Continuous delivery, CD, is a software engineering approach in which teams keep producing valuable software in short cycles and ensure that the software can be reliably released at any time. So I hope everyone can agree that one of their goals is to ship valuable software. I'm just going to gloss over that one. Short cycles, that means you want to be shipping early, shipping often, shipping as quickly as you can, and having that, okay, I have something cool, let's get this to our users, and okay, now our users can see that cool thing. Have that cycle be as small as possible. And then reliably released at any time just means don't break the build. You have to know that whatever is in this particular place in your code SCM or infrastructure, if it's there, it's okay to ship. And you want to keep that, make that be something that can be continuously updated. So this really means like don't break the build, keep master green, or use a production branch that's going to be green. So that you know that you can ship that at any time. You don't need to like ask everybody on your team, hey, can we actually deploy this? Is that okay? Is something going to break? So that's really all continuous delivery is. It just means you're always shipping. We actually have t-shirts out there that say always keep shipping. You can put one on and then you're continuously delivering our slogans. So what are our needs for a continuous delivery system? So the core attributes, at least the ones that I think about, are speed, parity, reliability, and flexibility. So what does that mean? For speed, for that CD cycle, that means that once you say, all right, I've got this stuff up on GitHub that I really like, let's get it to users, we got to check that code out. We want to run the tests or run the build or both, compile, build that deployment artifact, ship it somewhere, and then start it and actually boot it up. So what do I mean by deployment artifact? This can be a lot of different things depending on what you're doing in production, what you're doing with your local code base. It can be a binary, it can be a slug like Heroku uses. This could be a WAR file, it could be a VM. This could be like an AMI image, a container, a tarball, whatever it happens to be that you actually ship. So when it comes to parity, for me, this is like, it worked for me, like it worked on dev, the tests pass, we shipped it, now it doesn't work, like that's parity. Is it actually going to work the same way in all of the places that you're using it? And then reliability, let's just try running it again. Maybe it'll work the second time. We want to be able to run things each time, have them be working the same way over and over and over. So if on our local machines it passes, that means that it should be passing on CI, and if CI fails and you just run it again, then it passes, then you don't really have a reliable system. If you have to deploy a couple of times before it goes through, you don't really have good reliability there. And then flexibility is, I need X. Like, what happens when you need a new thing that you didn't need before? How hard is it to get that new thing in place throughout your entire pipeline? So what are the options for us to do continuous delivery? This was something we were looking at as we wanted to bring our application pipeline into this, really level up our operations. So if you look at past solutions, these are things like Elastic Beanstalk, Heroku, many others. They tend to be really fast because they've already sort of set everything up and built it all up for you. So you just sort of give them your code and they're really good. They have whole teams of people working on getting your code up and going quickly. The parity, though, isn't that great because when you're on your local machine, You don't like run your tests in Elastic Beanstalk and run your development server in Elastic Beanstalk on your own machine. At least if you did, and you went out to the cloud, that would be kind of painful. So it's kind of hard if something fails on a pass to bring it back down and figure it out. For reliability, they are usually pretty good because they have a whole team of developers making sure that exact environment is working fairly well. And then flexibility, this one, like you can get stuff into those different environments, but usually they don't do a great job because they have certain, like, here's the Ruby one, and here's the Go one, and here's the Java one. And to get more packages and more customization in there, you have to do a lot of legwork. So the next one is like configuration management. And when I'm talking about configuration management, what I specifically mean is when you boot up a pretty blank server and then you use one of these technologies to bring that blank server to the point where it can run your code. So in that sense, it's not great on speed because if you bring up a blank server, you then have to install everything, and that's going to be take that same amount of time every time, no matter what. The Parity isn't great unless you're actually using those tools on your own, development machine on your laptop, but you're not really going to use those on your laptop. So I gave this an X, but I would give it a check mark if you used virtualization technology locally and applied your configuration management tools to those virtualization technologies and then did your development in that virtual machine. So, but that's kind of a pain. Reliability, I gave it a check with a question mark because I felt like this kind of depends on you. How reliable are your apt-get commands? When is that Debian prompt going to come up and ask for some user input that you forgot to give it? Or when is your configuration file that you've put in there going to get out of sync with the operating system's version? So this is a lot of work, but you can do it well. And then flexibility, of course, that's why these things came about. They're great at flexibility because you get to set things up exactly how you want. So the next level up here is a virtual machine. And when I talk about a virtual machine, what I mean is that sort of full image snapshotting, like building an AMI on Amazon. So you might use a configuration management tool and create that snapshot. And then when you want to deploy it over and over again, you just launch your snapshot up. So in that sense, it's a lot more reliable because once you've got that snapshot working and you liked it, it's easier to create a new version of it. And you also have that parity as well because hopefully you can move that VM onto your local machine and run it in a virtualization technology. But the speed still isn't great. It's better, but it can still take like a couple of minutes to really bring up one of these new machines. Then we looked at containers, and they really, really fix that speed problem in a lot of cases. And of course, this is why I'm actually here at an event called Container Days, because if I didn't put all the checks next to containers, I might as well just not even give this talk. And from containers, there's still a lot of options. And for us, when we were looking around, Docker just added another check to speed. So I broke the rules of the checks and the X's just for Docker. And we'll talk a little bit more about that in a little bit. So why are we going to choose Docker here? It's not just about that speed. It's about how it brings a lot of benefits to all of those attributes. So one thing Jerome talked about yesterday was the caching layers and how rebuilds can be very fast because after you've run a step, if that same step is run again when you're running through a Dockerfile, it can use that layer on the file system and just reinvigorate it and move forwards. That's why you can pull down an operating system image pretty quickly and just run it and say, I'm going to start with Debian, and you don't have to spend like 15 minutes installing Debian. You can just pull it down and run it. If you do a package installation in the Dockerfile, anytime you go from Debian to that package in the same set of steps, Docker just flies through it and like fast forwards, just like Git would. I also think that Docker files are pretty great, and they've chosen to be very, very simple. They're completely flat. You can't use any logic constructs. And that, I think, also makes them very understandable. It's just this one script that you're going to look through, right? And it's a centralized place. You know you can go to the Dockerfile and see how a machine was provisioned. Now, of course, you can take this to another level, build your own tool, inject it into the Dockerfile, and then run a whole bunch of crazy scripts, and you can get rid of all of those wonderful attributes. But most of the time you don't need to do that if you've got something pretty simple that you're going to set up. So we really liked how with a Dockerfile you got this sort of versioned history that was very clear to read through. Even someone who's relatively new to ops and development can look at a Dockerfile and go, oh, it's just like running these commands and setting these variables. That's great. Docker also brings a lot of official and community images, so you don't have to reinvent the wheel. You can say, you know what, just give me Ruby, and it feels just like a pass. They have these on-build images for languages. If you use like Ruby on-build or Go on-build, you don't have to actually type anything in your Docker file. It will look at your current directory, assume it's a standard Ruby or Go project, include the source code in, and run the standard language commands. And if you have a pretty standard project, then you don't have to do any customization. And that's really cool. And then the great thing about Docker is you can take these images and you can actually read their Docker files and you can extend them, you can copy paste them, and you can tweak them. So you don't have to reinvent the wheel if you're doing something similar to what others have done. But of course you can, because you can start from bare operating system images or even from your own tar snapshots and build upon them. The other great thing about Docker is all the hosting choices. Everybody is jumping in the game on Docker here. AWS, Google, even Microsoft, which is pretty cool. There's really low lock-in here because if you've Dockerized your application and your services, you can take those to different hosting providers and you have to tweak your deployment scripts, but you don't have to tweak your application run environment and configuration. So that's pretty cool. And it's also, Docker's making it easier and easier every time to do this yourself. Things like Docker Swarm, Docker Machine are maturing and making this a lot easier. And there's also plenty of open source hosting choices like Deis, for example, where you can run your own Deis cluster and on your own machines, and then that creates a Docker environment for you to play around with. So that brings us to Docker continuous delivery. So I wanted to look at what our options are for doing something like this. So the first thing you can do to be delivering constantly is to do this off of your local machine. This is pretty much what everybody does when there's only one developer, or maybe a few developers that have really good communication between them. On my own laptop, I'm going to run my tests, I'm going to do my builds, I'm going to push my images, trigger my host pull. I'm just sort of doing it right here, and I can monitor it and tweak it and do what I need to do. And if something bad happens, I can just type a lot, and then that fixes things usually. But the problem is that, like, hopefully you ran the tests. Maybe there's somebody who's, no, not you, but like somebody else on your team who maybe just didn't run the test that time because they really needed to deploy something, and maybe they broke a bunch of stuff. And is it really that same environment? Because maybe you decided, I'm just going to run the tests on my local box instead of running them inside of Docker, and I'm going to say, oh, that's close enough. Building images, I mean, I don't know about you, but I kind of like thin laptops, and thin laptops are slow. CPU, the network, I mean, if you're on Wi-Fi at some co-working space, how long is that going to take? Pushing and triggering the host pulls to do the deployments, that can have race conditions with the other devs on your team. So you got to really be communicating about that stuff, because you could push, then they could push, but then they deploy and then you deploy, and who knows what's happening at that point. So then the next option is doing a hosted solution for continuous delivery. So you'll build your CI container, and then inside that CI container you can run your tests, and now you know that your tests are going to run in that nice environment. Build your production containers, push them, trigger that host pull. And by doing it on a hosted environment, all of your team members can go and look there, and the host will sort of serialize all of your work so that you can all know on the team what's happening. But there are some issues right now with hosted solutions out there. Caching is certainly an issue. Caching all of those Docker layers. If those layers aren't around from your last build, you got to start all over again, and that throws all of those check marks for speed for Docker right out the window, and it puts you pretty much on the same level of configuration management tool. When you're running your tests in a CI container, it's up to you to make sure that that CI container is actually has good parity with your production containers. So that's on you, but you sort of have to figure it out. And then for building the production containers, it still can be kind of tricky to build your build artifacts and build your production containers, especially when you start building multiple of those containers and pushing them up and orchestrating them. And then the third option is to do a custom solution, build something yourself. But I mean, who knows what that is, how it works. It's all on you at that point, and it's up to you to build it completely awesome. And usually people go with things like Jenkins or Drone here, but at that point, it's on you, right? So what are we missing across all of these solutions? Docker's a new technology, so for us, we really wanted to look at what do we really need in this space to do a really great job? What would we need to do the best job for Docker continuous delivery? So to have a centralized continuous delivery system, we had to think about our goals again. Think about those original goals, but also what do we want to be able to do with Docker to be able to have the best centralized system that we can. So that first one again is parity. So at this point, we're going to stop pontificating a little bit, and I'm going to talk about a couple of ideas that really helped us out here, and hopefully can help you too. So for parity, that just means you want your CI container to be as close as possible to your production container. In reality, you can try to get as close as possible. You're never really going to get exactly there because you're not going to want them to be exactly the same. You're going to want certain libraries for testing, maybe different libraries for production, but you always want to get as close as possible there. So having the same from in your Dockerfile can really help here. Having them both come from the same Ruby version image, as opposed to the production one being this CentOS image where you manually compile the Ruby patch level that you want with some patches. If you're going to do that in production, use that base in your tests as well. You can even chain these and say, this is my production image, and my CI image comes from the production image, plus here's some test packages that we needed to compile some extensions or whatever that is. The other thing is you really want to use all of the Docker linked services. That's also sort of how Docker Compose works. We'll talk about that a little bit more. But when you're building your containers, when you go out to production, even with non-containerized PaaS solutions, your services communicate over the network. They communicate with ports and environment configuration. So you're going to talk to your database over an IP, over a port. When it comes to CI, you don't want to then just make one big monolithic container that has a database inside of it. That's not representative to how your production system works. You want to actually do that over the network, and then you'll discover potential issues that could arise from doing it over the network versus having it all contained therein. And you also want your hosting stack to be Docker. So this is our goal here. We actually want to take these containers and go to a Docker deployment mechanism. We don't just want to use Docker for CI to give us a good CI environment. We have to go to Docker too. Otherwise, we're not going to see those same situations or not have that same kind of control. So our next goal with this is the orchestration around all of our containers, how that's going to work in continuous integration, how that's going to work during deployment and in production. So that means running tasks and linking services. So Docker Compose is really good at bringing up all of your servers, but we also, in CI, we have to run a bunch of commands, and we have to run those commands with all of our other services connected to it. We need our database, we need our cache, etc. And that's where Docker Compose's run comes in. It actually lets you run individual tasks instead of just saying, give me a service, you can run a command as well. But that brings us to multiple compositions. We may have a lot of different setups and environments for different kinds of tests. So for our unit tests, we might want to keep them quick and just run a small layer. But maybe integration tests, we need a particular service to work with. And then acceptance tests, we want to totally wrap up and black box our environment. And yeah, I'm leaving that as an open question that we'll work on later. And then speed. Clearly, this is one of the big goals from the start. It's one of the main reasons people are looking at containers now is to work on that speed, work on that continuous delivery cycle. And a lot of this is going to come down to caching. So for speed and caching, the base images are really important. We want to be able to use the layers from last time as well. So, sharing that base, layering on top, using those cache layers really helps us towards speed. So for layers from last time, Docker does this in a really natural way with registries. If you push your image up to a registry, it doesn't take that image, make one big blob of it, and send it to the registry. It takes all the layers that you use to create that image and sends all the layers to the registry as well. And when you pull it back down, that's why when you do a Docker pull, you see tons and tons and tons of progress bars, because all the layers are coming back down at the same time. So registries are a really natural fit for doing your caching. And then another one of our goals was parallelism. Whenever you get to a bigger project, everything starts to slow down, and being able to do things in parallel really can help speed it up. But it's really hard. But we have Docker isolation. And this is the same thing that you have from virtual machines, and containers bring that same thing. By isolating your different applications, by hiding which ports they're running on, remapping them, all that stuff, you can create really nicely isolated systems that are much, much easier to run in parallel. The trick then becomes the orchestration of all of that work. And that's because you have to orchestrate your orchestration. So if you're running things in parallel, but those parallel things are each using something like Docker Compose, then you need a Docker Compose composer. And that's where it all gets really fun. Orchestration of orchestration.
I think it's a marketing opportunity.
Yeah, right. I don't know. Maybe we'll just trademark it. This will be Ochestration by Codeship. It will be the name of our new product. It's a good idea. Thank you. So for parallelism, we might have a lot of crazy pipelines. We want to do that checkout, but then maybe we have a static analysis layer where we want to lint, do some style checking, security checking. Then when we go into our CI, we might have a couple of different builds we need to do to build up our container environment. So for our unit, we might be building version A for our unit layer. That could be really lightweight, run really fast. B, for our integration tests, those could be different for each of the different tests as well. And then C was for like acceptance testing, where we might have to black box it. Then we have to bring all that back together when they've all passed. If they pass, we want to continue to continuous deployment. And that's when we're going to have to potentially build multiple production containers and push those and deploy them together. And then if we bring all that back together and everything happens to work, then we deployed. And this can get pretty complicated. So even then, this is what I was talking about with the orchestration of orchestration, which is that the acceptance object, that one piece of that whole pipeline, may be an application with the test environment in it that links to some other API that we use, plus a database and a cache. So we've got a lot of layers here. So of course, we have to go build that now, because it doesn't exist. So this is the section where I'm really going to talk about what we learned, which means what we were trying to build it, and the assumptions we made that weren't true and had to overcome. So the first thing that you have to do when you're setting up this sort of pipeline is you have to define all of your containers. So that's sort of step one. That's what a lot of the workshops are here that you're going to be working on. That's sort of what you go through when you set up your first Docker container. You have to define them with those Docker files. And of course, like I mentioned before, the official language containers can help you a ton here. Even if they're not going to be your end game choice because they're not small enough or they're not specific enough, they're a great starting point because you don't have to relearn everything that those people learned to set it up. And like I said before, you can go to the registries, look at the Docker files, and you can copy them, you can pick them apart. So I would always say, use these if you can, because even if they're bigger, a little bit more complicated, they're going to be more reliable than something you built yourself because they've been around for a while and a lot of people are using them. The official language containers, they dictate the operating system because they control that initial from. You can't say, I want the Ruby one that's on Ubuntu, not the Ruby one that's on Debian, unless somebody has also made that version. But the official ones, they usually are coming from Debian, and you usually don't get to choose there. So you can't use the official Ruby container that uses CentOS. And the other downside with these, like I was saying before, is that they're big. So that poll can be particularly slow over the network. It also can use a lot of disk space. When you're using Docker machine virtualized, you have to manage your virtual disk space and how it shares that space with your host operating system. And that can get pretty annoying, especially when in your dev cycle you're building things over and over, you're pulling different versions. You have to do a lot of cleanup here. So what we wanted to work on here first is our containers for the continuous integration part, for the testing part. And in this situation, your code changes a lot. That's where all the churn is. Every time you commit something, that means your code has changed. So those constant changes are going to be something that we want to get really right with our CI containers, because that's all CI does, is it just pulls the next version and builds it again. And the majority of the time for this is often the dependencies. It's all of the Ruby gems, or all of the packages from Maven that you have to pull down, or all of the things you have to go get and compile. And so that can be a really big pain, especially when you've got, you're working in a dynamic language that has a bunch of whatever your dependencies are that build against like C libraries and bindings. Like that can take a really long time. But the thing is, the dependencies really only change occasionally. They don't change every commit. They only change every now and then when you do an update. So this brings us to hack number 1, which is layering your dependencies. So in a classic Dockerfile, what you're going to do is you're going to add the current directory. That means that everything in your project's directory is going to get put into the container. And when you do an add, Docker will create a layer based on those files. And I believe what they do is they use the modification times and hashes to determine whether those files are the same. So only if all of those files are the same will you be able to use a cached version of this add command. And then after that, you would first, no, it doesn't.
Does that change?
Yeah.
Oh, I'm very sorry.
yeah, and that's the thing why I'm not completely sure is because this is changing a lot. Originally, it always busted the cache. Then I think they did it with like file modification times, and then I think they started using like hashing functions. And honestly, I don't really know what the state of it is at this moment. I just know that this trick works, and that you can do caches on your adds if you're always adding the exact same stuff with no changes. So after you add all of your stuff, the next thing you usually do is you do your dependency management. This is your make dependencies, bundle, Maven, go get, all of that stuff. And then after that, your command for your CI container, whatever it is that runs your tests, will come afterwards. So if there's a small code change, you have to rerun this run command. With a layered setup, the first thing that you want to do is add whatever your dependency manifest object is. So in the Go world, this might be your godeps directory and maybe your make file to do the building. In the Ruby world, it would be your gem file and your gemfile.lock. I believe you can do this with Maven too. It's like the POM XML or something. I don't exactly know. But you add in whatever it is that says, here are all my dependencies, your code. Then you can run your dependency building, bundling, etc. Then you can add everything, which will give you that secondary layer for your own code. And then you can run your tests. And then if you don't update your gem file, for example, with a new version of your gemfile.lock, you can reuse that layer, and you don't have to redo your dependency builds. For me, I always think of Nokogiri. For anyone who does Ruby development, that gem takes so long to build. So with this dependency layering, you want to cache on manifest files. And there were times when we didn't have a manifest file, but we could use scripts and language introspection tools to build a manifest file in order to preload some of this stuff. So like in the Go world, there's like some Go tools that let you scan your source code. and it tells you what all of the remote packages are that you're using, then you can send those to the go get command and download them ahead of time. So even if you can't do a perfect job of like building everything, anything that you can prefetch, precompile, if you can jam that into another layer at the top, you can really speed this up. So this is really great on CI, but it is fantastic in development on your own machine, because when you're tweaking, like, okay, change that, add a little spacing, refresh the page, change that, refresh the page. If you have to rebuild your images, you want that to be insanely fast. Okay, so the next hack was registries for CI, because one of the things I was talking about before is that if your CI server doesn't actually have the layers from last time, it can't use the layers from last time. So for us, this meant that when you're going to be running those builds, you want to pull your application as it was built on the branch that you're working on from last time. By pulling it down, you are going to pull a little extra that you don't want, namely that final layer with your source code in it, but you also are going to get all the previous layers that went to build it. This is like priming your cache with the results from last time. And by doing this with a registry, you leave all that up to Docker. You don't have to like ship tarballs around and put them on S3 and take your .gem directory, your gem home or your like your Go path or anything, zip it up and ship it around. If you just use registries natively, this will get you there much, much easier. And all that really means is you're going to pull it down before you run CI and then push it after your CI is done. And you could even like background this after you do your builds or something like that and push it back in. You just want to tag these things with not production tags. So you can go ahead and add prefixes or suffixes or whatever makes sense for you, naming them so that you can keep those separate from what you're actually shipping. And then, of course, you want to run a registry near your CI. You can use the Docker Hub, but you don't have to. They've open sourced their registry tools. They're also launching, I think it's in the first beta or first RC of their new version of the registry. And there's other registries out there too, like Quay. There's even a really funny one called the Dogestry, like Dog, like the meme, that is a registry that you can put onto S3 and doesn't actually run a server. It's like a file store based registry system, which is pretty funny. So if you can put your registry near CI, that means that those pushes and pulls will be very, very quick. The last thing you want to do is be going like across coasts or countries to get to your data. And then for your production containers, you want to make these really close to CI. Again, this is not just about parity. In this case, it's actually about speed. The closer your production containers are to CI, the faster they will build because they can use layers from your CI containers. And of course, you can flip this around and say, if your CI containers are very close to your production ones, they can use the production containers build layers to build the CI containers. So keeping all of this stuff really close just has wins all around. So yeah, common bases, that's really useful. If you have like, you've got like API number 1 and it uses Ubuntu, and API number 2 and it uses Debian, and then our app, it's based off of CentOS, you're going to pull like 2 gigs just for that. So yeah, if they're huge, it can be slow to push, slow to pull, and slow to deploy. But if you've got a lot of layers, it can really speed that up. All right, so hack number 3. Now we're going to do some really fun stuff, and this is somewhat. I'm not going to exactly recommend this. I just think it's really cool, and I always want to share crazy techniques just to get people's minds churning over this stuff. So this was something really neat that we worked on that sort of throws a couple of the pieces of advice from before away, but can also give you some benefits. So this is a trade-off. Exercise your brains. So during CI, one thing we might want to do is build a production binary off of our system. This could be like an actual binary, or this could be like a bytecode, something like that. And then we'll do a Docker build of our production Docker file in the current directory. And then we might just take a bare OS, maybe install a dynamic library we need, and then inject just the binary in and run it. So what that means is we need a minimal number of packages to install in the operating system. We don't need any language packages, or maybe we just need that VM like the JRE or something. But this only works for compiled languages, so it's only somewhat useful. And then there's a little addition here, and this is just crazy, and I suggest that you try this out at some point just because it's really fun and makes your brain hurt because it makes you think about how different containers are from VMs. Scratch, if you don't know, is a Docker container, and it's represented by an empty tarball. It is the null container from which all original containers come from, and it has nothing in it. So in this case, if you make your production binary and you build, you say from scratch, you add your binary and you run it. And that's it. There's actually nothing else in there. It's just your binary. So these are hilariously tiny. We're actually running in production a couple of Docker containers that are in single digits of megabytes. So 6 megs, 9 meg containers. It is just pretty funny. So this only works for statically compiled binaries. It also has the worst CI and production parity because unless you're running your tests with a statically compiled production binary with no debug symbols, you don't really have that parity. So again, like I said, this is throwing out some of the previous advice, but it's also really, really cool as an optimization. And it's near instant push, pull, boot, deploy. How fast does it take one Amazon machine to send 6 megs to another Amazon machine? It's like almost impossible to measure that, you know. But one thing that we can do that gets us sort of in between these techniques are minimal guests. So what do I mean by that? I mean you want a really bare OS. You don't need all of Debian or all of Ubuntu just to run some language code. That means you're going to have a minimal tool chain and really minimal packaging and maybe even some DIY packaging, you know, pulling down your own code. So these are really small containers, and this is really helpful for the dynamic crowd, you know, Ruby, Python, all that good stuff, JavaScript. So there's one promising project I wanted to point out, and this is the Alpine container project. It's based off of Alpine Linux, which isn't affiliated with the containerization of Alpine Linux, but it's a really small guest that you can use. So if you come from Alpine and then you use their APK package manager to install MySQL, you can actually have a MySQL client container that's only 16 megs. And that's pretty cool, and that's pretty small. And they have this package manager, but you know, it's not the most amazing package manager, but it's got plenty of good stuff in it. So I think this is just one example, and I'm hoping that one thing we're going to see in the next year are lots and lots of different options for these minimal containers. Because even Debian is like, I think it's around 180 or 200 megs or so, and Ubuntu is a little bit more than that. But I mean, Alpine's like 6 megs, and it actually has a package manager, so that's amazing. All right, so this is bringing us back around to that orchestration problem. So we're using, or at least we tried to use Docker Compose. And the way that you do this, and we'll talk about this more in some of the workshops, so I'm not going to go too crazy here, but you can define your application. Really, it's just another service. And you can link them together and link their ports. And then you can do things like, say, run my app with make test. And it will actually bring up Postgres and link it to your app to be able to run those together. But we did have a couple problems with this. One of them is specifying different Docker files. I'm not sure if they've actually improved that since we worked on it. You also can't really tell when services are running. Compose considers things running when their process starts, but not when they're actually available. There's an open issue on Docker for this, but like it's probably not solvable because how do you really know if something is up and running? So maybe there'll be some sort of check back system, but they're working on it. We also don't really have good environment variable encryption management type stuff. You sort of have to do this yourself. And you really can only have one Docker Compose file. So once you start composing composes, you either have to have one big crazy file with a lot of namespacing and stuff, or you got to break things apart into directories. So for us at least, what we're doing in the meantime is manually running and linking all of this stuff. So that means that we're going to run our Postgres, we're going to sleep for a magic number with a frowny face on it, and then we're going to run our app, run the make test, and then we have to observe that one's exit code and then kill Postgres. So this is still pretty tricky, but we're working on it. And then, of course, our good friend Parallelism. So we have to run and link and actually namespace all of this stuff to be able to do it in parallel. And really this comes down to having to run your own agent, split up the work, monitor all of the containers. Yeah, so this is the fun stuff, right? But we'll figure it out. We're working on it. Docker Swarm is also really cool here because if we have this sort of system where we're working and using Docker's own tools, if we're using just Docker and we're using the Docker host, Swarm can make one host, make it look like one host when it's actually driving many machines. So if we can build CI and CD pipelines in parallel around this, it should be relatively easy to run lots and lots of machines and run our containers spread across all of them and be able to scale that up incredibly highly. All right, bringing us to deployment. So there's a couple of different ways we can actually do our deploy with Docker. The first one is you push your code to your hosting provider and they build up the images. This is how one way of using Elastic Beanstalk works. This is how Deis can work as well, and there's a couple others that work that way too. The second one is you build and push your image like to a registry, and then you tell your hosting provider to pull it and run it. And Elastic Beanstalk can run in this mode. Elastic Container Service, Google App Engine, they work like that as well. And then you can also build up your Docker containers, but then cross-build them for your host's specific platform and push. And this is like what Heroku's beta Docker release does. It turns images into slugs. So if you're building on the host, that takes the burden off of CI, because CI can just push your code up and let the host build it. But that means, for the most part, with most hosting providers, these have to be single Dockerfile applications. You have to be able to deploy them on their own, because once you send it to your host, it's going to go. They're not going to be able to use your local cache, so it's not really as good. If you're going to build and push those images and trigger a pull, then you can use your local cache. CI is going to have to do your production builds, but that means that CI can also make sure that everything builds before anything gets pushed. But it does mean that push-pull can add some time because you have to ship all of that over to the host, as opposed to just sending a little bit that's your code and having it build it over there. But you can push a lot and launch a lot. The build and cross-build stuff, this is all very new. You really have to look into how each one is individually doing it. There might be some really interesting stuff here, but it also makes me wary because it's not really using things in a natural way. It seems like it's more of a shoehorn approach. But it could give you a nice blend of PaaS and DIY pros and cons. So fourth hack here is to, well, use the same registry. So if you've got your registry near CI, you can push your CI layers to the registry, just like we did before for our own caching, but now you can tag them for production. And that means that when you're actually pushing for production, only a few small changed layers are going to get pushed up. And then you put your registry near your hosting provider as well. So when they pull, they only need to pull what was changed since last time. And if they do have to pull everything because they don't cache, at least it's very close by and the pull will be fast. So you want to keep those common bases in your registries. You want to use similar bases and keep them all close together. And for us, this meant Amazon all the things. But you can replace Amazon with whatever your cloud provider is. All right, so what's next for us? Where are we still going here? What's unsolved? Better parallel tooling, clearly. Docker Compose is good at building a development environment. It's good at running tasks, but it doesn't quite have that ultra abstraction layer to let us do a lot of things at the same time. And maybe that's not Compose's job, but it would be cool to see more things in this space. Better development environments, being able to do a better job like syncing your code sort of hot when you're running your containers so that you can really be moving quickly. If we can get people to actually write code constantly by using containers, that'll give us the best parity from your development machine across your entire pipeline. And then better machine provisioning. So Docker Machine right now is a CLI, but it's not a library yet, which means it's kind of hard to automate because you've got to shell out to it. But being able to orchestrate your physical machines or physical VPSs through the same tools that you use in CI and in development means you're going to get that host level parity across the entire system. So that's something else we're also really looking at. Okay, so that brings me to the thing that I have to do, which is plug our awesome private beta. We're doing some really crazy Docker stuff with CI and CD. We solved a lot of these problems for ourselves for CI and CD, and then it's becoming part of our new product. And we've got some crazy things that mostly work that are cool to mess around with. So if you're interested in really pushing some of this stuff, you can chat with me or visit our booth and chat with Kurt. Okay, thank you. My timer just said 45, so I'm sorry I had to rush the end a little bit to get there. Are we okay to do any questions? Sure. Okay, yeah. Awesome.
Hi.
Cool. Well, I hope it's because I explained everything perfectly, not because everyone wants to go eat lunch.
That's cheating.
Some people talk about at the end of your build pipeline, you should squash your image so that it's only one giant image, because then you know you have the same thing as the build artifact. It seems that your opinion is the opposite of that because you want to take advantage of the layers and speed. Can you talk a bit about that?
Yeah. So I mean, I think this just comes down to another trade-off that you're going to have to choose between. If you have a lot of complicated setup that's going to yield a large image through a lot of steps, then the layers are going to be really helpful because you can use as much of the, and that's going to work if your hosting provider can also make use of those layers and pull and is caching. So some hosts can and some hosts can't. So if your host can't pull off of your layers, then squashing makes a lot of sense because you want to ship the smallest individual thing over there, not all of the intermediate layers. So those hosts, that might be a better solution. If you're running something that's more like DIY, where you're going to pull from something local and you can have that configuration ability, then the layers make more sense. And then there's also the crazy scratch containers where it doesn't really matter anymore when they're small. So, that answer?
Okay,
cool.
Yeah, and I mean, just as a personal thing, my talk, so I don't want to jump in too much, but it depends also on the frequency on which you're doing something. That one was the thing, but we've had like that works if the frequency in which you're trying to update them is low compared to application scale. Trying to commit, if you're doing a build once a commit or something like that, as you do in CI, if you're committing every couple of minutes, maybe shipping hundreds of megabytes every couple of minutes is not exactly a particularly a lot of type to make that work.
Yeah, there's a particular tipping point when your dev cycle, like your CD cycle, actually takes longer than when your builds come through in your source control, right? And that's when you go into like CD debt, when you're committing stuff faster than you can actually ship it, So as long as you can avoid that like swapping of CD land, then you're in a good spot. And I had a chat with somebody who was like, oh, I can just use Docker volumes and I can put all my dependencies on the volumes and I can ship them around. And then why stop there? I'm going to put like packages in there and then I'm going to put my code in there. And then it's like, well, if you're just using volumes, you're just doing VMs. Like it's the same stuff. You're going to want to use configuration management tools, use persistent volumes, and you're not really taking advantage of the immutability and repeatability that Docker is bringing. So if you want to go into the Docker world, you just got to embrace it and all of its benefits and all of its flaws. Otherwise, you're just going to be keeping a lot of the downsides of what we've been doing before and trying to jam them into this new style.
One of your optimizations was to use Docker Alpine, which is really cool. Did you guys look at BusyBox, and can you compare the two?
Yeah, so Alpine's got a package manager and a bunch of built-in packages, and we don't actually use it. I've just played around with it. That's why I put it in there as like a interesting project to watch, and I think it's an interesting pattern to watch too. Just that style of having minimal OS but with package management, especially if it allowed you to do your own packaging in a neat way so that you could have like across your organization, you could maintain a couple packages, but then a lot of different teams could reuse those packages, that sort of thing. The BusyBox container just has the BusyBox tools in it. So you still are going to have to like do a lot of wget, compile, tar-based installation of stuff, which lets you do it.